Hello everyone, today we'll be trying to tackle a problem. This is the problem, and here we have a spring constant K, and the spring was initially in this state where it was unstretched. Okay, and the final state is this. So there is no change in kinetic energy, and thus we have to find the work done by this force. So let's start. There are two kinds of forces here. One, gravitational, and the second one is spring force. So I will try to draw two diagrams like this, and each of them separates two types of forces, right? This one is for spring force and this one is for gravitational force. If we try to look at the spring force, then we need to find the displacement from the initial position, meaning the unstretched position. If we have to find the spring force, then we have to understand what the displacement is from the equilibrium position or unstretched position. As we have already told, that the unstretched position is the initial position, which is here, and this, as you can clearly see, it's a part of a circle, and the displacement will be this arc, which we will call to be x, and this x will be equal to radius times the angle that it's making with the horizontal. Okay, the force with which the spring will pull the box will be kx, where the x is this, and the direction of the pull will be tangentially in this direction. Okay, next let's go to the gravitational section, and there is another information that's missing here, which is there is no friction. So there's no friction involved here. We will be decomposing mg force, or the gravitational force, into two perpendicular components, which are mg cos theta and mg sin theta. And as you can see, the normal force from this ground, I mean this surface, to this box will be equal to n, and it will be cancelling the sine component of gravitational force. And there will be another equilibrium in this direction, which we will call the x. We will consider this to be the x-axis. So summation of f in x-axis will be equal to, we will consider this positive direction and this negative direction. So positive f minus mg cos theta, and they will be equal to 0. So we'll see that f will be equal to mg cos theta for every theta that's possible here. So far we have only considered the gravitational force and the spring force, both, but individually, not at once. In this situation, the scenario is different. There is both spring force and gravitational force that's acting on the body, as well as the force F and this normal force N. We don't need to consider the perpendicular forces like N or mg sin theta, but we have to consider the force that's acting in this x direction. Okay, so the total force that will be acting in the x direction, positive and negative, will be F mg cos theta kx, and we have to make a combination of these, not individually but simultaneously. Now if we try to draw a free body diagram of this object, this will turn out to be something like this. Okay, so as we can see, if we put two equilibrium conditions in x direction and y direction, positive, negative, positive, negative, we will find that summing in this x direction it will be 0. So we have considered this to be positive direction and this to be the negative direction. So this will be positive f minus kx minus mg cos theta, which will be equal to 0. And we have already said or showed that x is equal to a theta. Okay, so f will be equal to k x, and we will replace it with a theta and plus mg cos theta. So we have found a function f with the variable theta. Now we can calculate the work done. Put up the equation dw is equal to f dot ds. Okay, so the force is in this direction, and of course the displacement will be in this direction as we are moving this box upwards. So ds will be also in this direction. So f dot ds will be equal to f ds cos 0 degree. So it will be equal to f ds. Okay, so then we can continue to work with this. dw will be equal to f, and we can replace f with this k a theta plus mg cos theta and ds. Okay, so we can draw another picture. The picture is that, okay, this is the portion of the circle and this is the box, let's say. Okay, so if it has gone from here to here and this displacement is ds, and its angular displacement, let it be d theta, and its initial position is, of course, not initial position, its current position is of course equal to theta. Let us consider that. Okay, so we can see that ds is equal to a d theta. Okay, so we can substitute that. dw is equal to k a theta plus mg cos theta a d theta. So if we just now try to integrate, w is equal to integration of dw is equal to integration of ka square d theta, or actually ka square theta plus mga cos theta d theta. So the variable is theta. So the initial, from where we are going to calculate work, the initial state was here. The initial position was here. So the initial position, theta was equal to 0 initial, and at the final stage the angle was taken to be beta. So theta will be equal to beta when it's final stage. Okay, so w will be equal to integration from, okay, I can take the limits here, bounds beta. Okay, then if we try to integrate, I will directly give the integration result. Ka square will come out from the integration, and theta will integrate to be theta square divided by 2 plus mga. All of these are constants, and cos theta can be integrated to be sine theta, and of course we can put the limits, I mean bounds, 0 to beta, 0 to beta. So work done will be equal to Ka square beta square divided by 2 minus 0 square divided by 2 plus mga sine beta minus sine 0. W is equal to Ka square beta square divided by 2 plus mga sine beta. That's the answer. That's the final answer, I mean. That's it. Bye everyone. Thank you for watching. See you later.